Oh, hi there. Thanks so much for showing up for your math learning. It's Tutor Grant, and we're going to take a look at the mixed questions from the intermediate curriculum, Math Mastery Academy. Let's go, everybody. Let's dive in. Use this video to get unstuck. Once I unstick you in a question, pause the video, finish the question yourself, and then turn the video back on to check your solution. Okay? So that's, I think, the best way to support your learning and to learn from any mistakes or places where you get stuck. All right, let's keep going. Okay, so the multiple choice questions start with this nice question here. We have a voucher and there's 4 characters. All right, so there's 4 different places where we're going to get options. The first is a letter V, X, or P. So we have this position here, V, X, or P. There are 3 options in that spot. The second and third are different digits. So we're going to put this in here. So the second and the third are different digits. So we'd have 10 different options there for that first choice. But then only 9 there because they have to be different. All right. And then the last one is the number that we get when we multiply these two together. So how many options do we have here is a good question. Options? Well, there's lots of different things that could be. When we're multiplying 2 numbers together, it could be literally any digit. So really we have like 10 options? No, we only have 1. There's only 1 option there because we've already made that choice. We've already made that choice, at least in our thinking. So this one actually doesn't add any more codes to the number of vouchers. So we just have 1. And so then to find our answer, we just multiply here. So this is 30 times 9 is 270. This will be the answer, 270. Okay, that's how you do that. All right, let's keep going. All right, now let's consider this question about a die. One way to answer this question would actually be to use a 6-sided die and experiment. You're at home, you can do that, and I think that's going to build your visualization skills if you're struggling on a question like this. But if not, then I don't know if you can bring one into the IMC and consult an actual die. I don't think so because it's not specifically listed as a thing we're allowed to do. So anyway, one thing we could do is just take like an inventory of where things are, right? So 1 is facing east. Okay, the die is then moved 4 times, rotating it each about a 90-degree angle about an edge. So we're going to rotate it down so that the 1 is down. So we could do like a table like down, face, and then what's going to be east, what's going to be facing us south, and what's going to be up. Okay, and if we do that, we can use our visualization here just to really keep track of it. So once we turn that 1 down, then the one that's facing south is still 3, the one that's east is now 2, and the one that's up is 6. And then what are we going to rotate it around? We rotate it around 2. Okay, so we tumble it one more time. So 2 is now down, 3 is still facing south, and 1 is facing that way. We can't see it. But now facing east is 6, and well, 2 is down, so 5 must be up. And we can use this idea that sides that are opposite always add to 7 to kind of keep track of things as we go through. Then we're going to rotate through face 3. So we notice that face 3 is facing south at this time. So we're going to tumble the die now towards us. So 3 is down and 4 is up. And then if we have like moved that way and then tumble it towards us, whatever was east stays east, so that's still 6. But then moving the die towards us, it's whatever was up is now facing us south, so we're now 5. And we can just use this table to keep track of stuff, and then we're going to move this around. So we're going to roll this one more time towards us. So if 5 now is down, so we're going to roll now 5 to be down. So down 5 is down, 2 is up, and we're still rolling the dice towards us. So south is coming towards us to go down. That means 6 is still facing east, 1 is facing west. So that's how we can use that one. And we use that idea of tracking the 6-1 connection because they sum to 7. So they're on opposite sides. That's how I would do that one. All right. And it's facing south of B4. So our table is complete. That's how I would approach that question. Okay, well, let's keep going. Let's consider the next multiple choice question, the final one. So Beatrix has this desktop clock. It's digital, and it displays the numbers reflected in her glass tabletop. So we're very interested in things like, 1308, which are both Fibonacci numbers, so they've clearly been chosen for that reason. And when they're reflected in the glass tabletop, the 1 reflects as a 1, the 3 reflects as a 3, the O reflects as an O, and see how the reflection, it's the same. So we're interested in these types of numbers that have a reflectional symmetry, a vertical reflection, that are symmetrical in that way. And we want to know how many times have this property. So we'd like to know which digits can do that. 1 can, 3 can, 2 can't. 2 becomes like, if I reflect 2 here in a mirror, it becomes like a 5. Okay, so they don't register the same time, even though you could read it as a time. Okay, so 4 doesn't, 5 doesn't, 6 doesn't, 7 doesn't, 8 does, 9 doesn't, and 0 does. Okay, so these are in fact the only digits that have that property. So, how many different times exist on the 24-hour clock that do that? Okay, well, and we have these positions to consider. All right, and then dot dot and these positions. Let's think about the minutes first. Okay, we can have any of those numbers here. So there are 4 numbers there, and then we can have 1 and 3 and 0 there, but not 8. So we can have 3 options there. Right? In this place, we can have actually all 3 options, and we actually get the number 1 twice. Okay, so this one is tricky. This digit is tricky because we have to consider it when we have 0, and we have with every combination here, we don't, it doesn't matter. We just need to see how many times we have it. The reason I'm talking funny right now is I'm realizing I got stuck a little bit because I realized sometimes when we have a 2 here, we don't get all of our options there. We only go 1, 2, 3, 4, and then go to the next day. But we don't care about the number 2 when we have a 2 leading this time, because we're not counting those anyway. So because when we lead with a 0 or we lead with a 1, we still get all of the other digits. In both cases, we can count all those. So here we can have a 1 or a 0, so we have 2 options there. And here we can have a 1, a 0, a 3, or an 8, so we have 4 options there. So now we multiply all these numbers together, which is 2 times 4 times 3 times 4. To find the total number of options, we just have to multiply the different options at each place. So that gives us the number 96. Ding, 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 ding. There it is. Okay, let's go. So that's how I would count those. I'm definitely not wanting to list all 96 options. Now we get to our Olympiad questions. So now we have to use great words and sentences as well as solid mathematical communication. So let's go. All right, we've got this chessboard with 8x8, this is an 8x8 grid, and we want to know the biggest circle that can be drawn that's only on white squares. Okay, so one of the first realizations that we want to make is that we have to have these circles passing through the intersections. That circle there that I just drew, which passes perfectly through and doesn't touch any black squares, but is always on white because it just goes through the intersection. Okay, that is bigger than this. Beep. There's a circle that's only on the white. So there, is that the answer? It would have a radius, right? If I look at that, here's my black circle, and I shade that in. So this is my black circle. And then I look for how would I find the radius of this circle. Ooh, I'm really drawing it poorly. Ooh, okay. We know it's not immediately apparent what the radius of this circle is. Well, the thing that we do is we just go in there and we say, okay, we start here, we go to the corner, that's our radius. It would be 1 on root 2 would be its radius. Okay, if this is 1 here, then that makes a right angled triangle. And so this one is also the radius, which is 1 on root 2. 1 on root 2 squared plus 1 on root 2 squared is 1. But we can do better. We can get a bigger circle. Okay, so how do we do that? Well, let's take a look. Certainly not that one. It's not that one. But while you're going, you're going to write down the things you notice. We note that any circle that is on more than one square must pass through the intersection between squares, or else part of the circumference of the circle would lie on black squares. There. So we make that observation. That's important to get all of our points. Okay. And then we can actually, in these questions, it's not only important to find the biggest one possible, but to prove that it's the biggest one possible. And so now, one thing that we can note is that there is no way to do this. There's no way to go like through this corner and that corner and that corner. It's impossible. That would make a straight line. And that's like a circle with infinite circumference. Like, yes, I could say at infinity it turns around and comes back and goes through there. But no, that doesn't make any sense. So we should make a note of that. And we should say, we also point out that it is impossible for a circle to pass diagonally through 3 consecutive points, as this would form a straight line and there would be no curve to our circumference. And it wouldn't be a circle. I don't know. It seems obvious. Of course it's obvious, but I like to say the obvious just so I make sure I get all the points. Consecutive. Straight should be spelt correctly. That's a math word. All right, let's go. So now let's see if we can pass through 2 of those and then like curve around. So what would that look like? We can try it over here. So let's just choose this one and this one. And then we see we could go through here and then do the same thing over there, and then go here and do the same thing over there, and then go here and do the same thing over there. And then this would be our circle. So there. Beautiful. Well, I think it's beautiful. You may not think it's beautiful. Okay. So, and now we're going to mention like the circle drawn on the left passes through 2 Now we have to find the radius, okay? So now I would go ahead and just re-diagram it. And so I'm just going to re-diagram the 4 black squares that we're encircling. So I'm going to have just a line there, a line there, a line here, like this. And we have this type of shape here. where our circle passes around these black points. Like so. Okay. And then let's go ahead and draw our circle again, as well as we can. We are allowed to bring a compass to these events, but I don't think you want to plan on using that if you're not tending to use that in your regular math practice. This diagram, I mean, I don't know. This diagram is okay-ish. All right, so now let's find the radius. We're going to go from the center here, and we're going to investigate one of the radii that falls to a point, because we're going to be able to investigate that. So just going to use a thicker marker here. Here is the radii that I'm going to look at that goes over there. And then we might just show the Pythagorean triangle that we can investigate. Okay, so that is, just checking our question. 8 by 8 grid of the size of each square is 1 centimeter. Okay, so this is 1/2 centimeters on that side, and then down here this is 1 1/2 centimeters, and this is x centimeters up here. So now we just say here. So I'm going to change. I don't like that I used x for that. I would prefer r. So r is better. So r squared is equal to 1 on 2. Put these in brackets squared plus 3 on 2. Put these in brackets squared. R squared is equal to 10 on 4. So r is equal to 5, but the square root of it on 2, because we're going to take the square root over here of both things. All right, then we get root 5 on 2. Root 5 on root 4. Root 4 is 2. So then we just finish up by saying, let's get close. There, and that's how that one do. So when you're wondering about that, that's how it's done. I had some heebie-jeebies there because I have an error here. I don't know why I divided 10 into 5. It's just 10. Weird. Okay, so when you're taking the square root of 10, the answer is it's the square root of 10. It doesn't become 5 just because it's on 2. So that was weird. Sometimes I do weird things when I'm talking about math as I'm doing it. That's often my excuse, but that was a very strange thing that happened to me there. So anyway, let's carry on. Let's keep going. Okay, so now we're talking about gorgeous grids. Nigel is going to be filling in these 9 by 9 grids, which might remind you of Sudoku. And if you don't already play Sudokus, then you might start, because a lot of questions have a Sudoku feel to them in these maths contests. Anyhow, so we're going to have these grids that are 9 by 9, pion pion, with 9 by 9 little things. And he's going to write 1, 2, 3, 4, 5, 6, 7, 8, 9 in order, but he starts at one of the digits and returns to 1 after 9. So that means he could go 7, 8, 9, 1, 2, 3, 4, 5, 6. Okay? So there's how many ways that he could do each line. Okay? Well, he's got 9 rows to fill in along here. And each one of them, once he's chosen the first number, let's say he starts with 7, He's done making choices in that line. So the rest are all determined. 8, 9, 1, 2, 3, 4, 5, 6. And that line would be done. So how many choices does he have at each point? He has 9 choices for each row. So let's just write that out. 9 choices there for that row, 9 choices there, dot, dot, dot. There's 9 times that he's making 9 choices, so that is 9 to the power 9. This is the total number of grids that he can create. Okay. Now, we're actually given that number. We want to know where it came from. That's where it came from to help us understand the question. So now, how do we make a grid gorgeous? Well, a grid must be gorgeous if the numbers along the rows add up to a number that's divisible. Oh wait, the 9-digit number that's read along that row is divisible by 9. Well, and also that the 9-digit number that's read down any row is also divisible by 9, and the numbers on the diagonals all must be divisible by 9. Okay? So how do we check that? Well, let's start by noting okay, well, every row is already taken care of. So we don't need to worry about rows. Rows are always fine. Now, let's say suppose he has some arrangement of numbers in the first 8 rows. Okay? No matter what, every column still can be satisfied this way. So that takes care of that first column. But one thing you'll notice is once that first column is taken care of, every other column is taken care of. Okay? Everyone. All right? And we can explain that with modular arithmetic. So what does that look like? Okay. 9 mod 9 equals 0 means the remainder 9, when divided by 9, gives remainder 0. So 9 mod 9 is 0. And 1 mod 9 is 1. Dot, dot, dot. Okay? So it wraps around. Not only the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, but it also wraps around with modular arithmetic. So we're always climbing the number that we are like a multiple of 9 more than. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, 2, 3, 4, 5, 6, 7, 8 in terms of how much it's toggling the divisibility by 9. Okay? Yeah. This is true for each column. So the second column So since, like, for example, we might show it this way. This one is just like, it's really hard to show. It's really nice to understand. It's really hard to show. So this is challenging. So we can look at it like this. You might actually draw out a grid. In fact, in the official solution, I'm just going to show you the grid in the official solution, but you could do it this way, where you'd say, consider the following grid, where we would have like, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then do the next one, 7, 8, 9, 1, 2, 3, 4, 5, 6, for example, and then just go dot, 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 because we just want to explain an idea. If we look at that in mod 9, this grid would look like this. Still, 1 mod 9 is 1, 2 mod 9 is 2. These are the remainders when we divide them by 9. And 0. And then we have 7, 8, 0, 1, 2, 3, 4, 5, 6. And we can think of these things in mod 0, and we get this different pattern, right? So 9 is, like 10 is the same thing as 1. It's the fact that we're like wrapping around there is the same in modular arithmetic as if we just carried on. There's another like thing that you can play with in your explanation. So anyway, so the point that I'm making is, or struggling to make, is that once we note that there will always be a choice in that first cell, so that bottom cell in that first column, that will make it fit and make that whole column divisible by 9. It's exactly one choice for us. Every other choice going forward has already been made. Okay, so let's consider one gorgeous grid that works. And this is a useful one to think about. The 1, 1, 2, 3. I'm going to pause and draw it out. So here's a very simple, gorgeous grid, and it's gorgeous. Okay, it's not beautiful, but it is gorgeous. All right, so the first column we got here, and we were 8 was our digit sum, so we needed exactly 1 to make us divisible by 9. There was only one choice there that would work. In this column, our digit sum is 16, so we need 2, of course. Here our digit sum is 24, so we need 3 to make 27. And it always works, and it always will. If that first column is divisible by 9, then every other column will be divisible by 9. Everyone. Okay? And there always exists that one choice there. So now let's check the diagonals. So here we go. We are 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice what happened there is that we end up in a situation where we already knew this column was going to be divisible by 9, but then we messed it up. We had 1 more than we needed. We had 2 more than we needed. We had 3 more than we needed. We had 4 more than we needed. We had 5 more than we needed. We had 6 more than we needed. We had 7 more than we needed. And then we had 8 more than we needed. So we basically had 1 plus 2 plus 3 plus 4 plus 8 more number than we needed, which totals 36, which is itself divisible by 9. And by the same argument, if we look at this column, that one was working because we made this special choice here. So because that column is working, oh no, we got 1 less than we needed, we got 2 less than we needed, and we get minus 36, which is itself divisible by 9. So always works for the diagonals as well. Okay, so then we go about explaining that, which give me a moment, I'm going to pause and do just there. So this is how I would explain it. It's so awkward to explaining this question because of the wrapping around from 9 to 1, but it doesn't change anything for divisibility by 9. It's just like, the same as going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. In mod 9, they're all 10 is the same as 1, 11 is the same as 2, and so on. So it's just tricky to explain it, and this is how I would explain it. So you note that that first column has this digit sum that totals a divisible by 9 number because we decided it would, and then this would be 1 more, 2 more, 3 more, and so on in terms of mod 9 than the previous row. And so that pattern continues, giving us 36 more than the first column. And because the first column was divisible by 9 and 36 mod 9 is 0, like it doesn't change at all, the divisibility by 9, since that column was divisible by 9, that diagonal would be divisible by 9. And then we can say the same argument. I think it's called the anti-diagonal. And the number in the final column. So now we've proven that if we create this gorgeous grid, which has this row, so that column, and all the rows are already taken care of. If that first column is itself divisible by 9, every column's taken care of, and both diagonals are taken care of necessarily. So that means that we can finally push this problem across the finish line. And we would say, thus, there are 9 raised to the power 8. Why 9 to the power 8? Because we can choose, I'm going to use another color here. We can choose whatever we want, 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 whatever we want. No choice there, only one option. So we had 9 choices 8 times. And then our last choice was constrained. So 1 out of every 9 grid is gorgeous, and there are 9 to the 8 gorgeous grids. Woof! It's a hard question to understand, but it's harder to explain. So I hope you like watching me squirm, everybody. I hope you enjoyed that as much as I did. Okay, final question. Let's go. We've got this bag full of 7 red discs, 8 blue discs, and 9 yellow discs, okay? And we're going to toss them all about. All right, 2 discs are drawn at random from the bag, and if the discs are the same color, then they're put back. However, if the discs are different colors, then they're both removed and one of the other ones is added. Okay? So this procedure is repeated until there's only 1 disc left in the bag or only the remaining discs in the bag have the same color. Okay, so let's take a look. So here's what we need to notice. There's something special about this. 7 red discs, 8 blue discs, and 9 yellow discs. We're going to do this process until there's only 1 disc left in the bag or all of the remaining discs in the bag have the same color. Okay? So let's explore both of those options. All right, first, how would we get all of the discs to be the same color? Well, color is the last disc or discs left in the bag. So we note that there is an odd number. I can just type here faster. Okay, so that's just like a first, just notice those numbers. There's 7, 8, and 9. It's too odd, too even. Okay. We're just going to go down by 1 each time. However, we also note that in no cases when we remove discs, we do change whether that number is even or odd, but we'll never get blue to be odd at the same time as either yellow or red. We'll never get red to be even at the same time yellow's odd, and vice versa. Red and yellow are fixed together. They have to both be odd or even at the same time. Let's prove it. Okay? So if you were stuck about that, then figure out how to prove that. So we can do that in cases. Case 1. Red and blue. So if we remove a red and blue, they're both taken out. So we now have 6 red, 7 blue, and then we add a yellow, 10 yellow. Okay? And notice, even, odd, even. Okay? Let's do case 2. Remove red and yellow. Then we would have 6 red, 8 blue, sorry, not 6 red. We'd have 9 blue because we add a blue. That's why we have 9 blue. And then we would have 8 yellow. And then in case 3, remove blue and yellow. And now we note that we would have, so we have to add a red. So we would now have 8 red, because we had 7 of them. And then we'd have now 7 blue and 8 yellow. Okay? So in none of these choices, and that's all the choices you can make. You can only remove a red and a blue, a red and yellow, or blue and a yellow. Now we've proven it when they started in their current orientation, but we can then just note that no matter how much you continue this pattern, the odds, the red and yellow are bound together to be odd and even at the same time. Blue, on the other hand, is never odd nor even at the same time as red and yellow. They always toggle opposite. Always. Okay, so now it suffices to say the only condition that ends the game is when two piles have been exhausted. The only piles would be 0 even at the same time are red and yellow, leaving some number of blue discs. Oops, I have a mistake here. This is impossible. I just said it wasn't possible. 5. There. So tidy that up. So that's our only ending condition, is ending where these are both even numbers and this is some odd number that's left over. Whee! Okay, so just to celebrate my mistakes, let's take a look at our mistakes. One of them was, oh my goodness, trying to explain this question is a real challenge. I think modular arithmetic really helps. I have one other mistake up here where I took the square root of 10 and it became the square root of 5, which is simply not true. The square root of 10 is the square root of 10. So I'm not really sure what happened there. But my diagram is right, the math was right, and for some reason that just moved on me and changed. And then I was like, wait, something's wrong. And then I figured it out. So that can happen. Listen to your gut. Okay, I hope that was enlightening. If you still have any questions, hit us up in the homework thread or ask your classmates or things. Bye for now, everyone.